This third session of CASS will focus on how to do function calls in Risc-V. To do function calls, we will heavily rely upon the stack. Now let us first take a step back to our first session. Look at C. This is some C code, and in C we have this concept of functions. I think everybody knows by now what a function is. Functions have some parameters, have a return value. Some languages you can have multiple return values. And this concept of a function is very important in programming. It allows us to modularize our code. For example, one of the great things is that we can execute printf and scanf, and we never wrote those functions ourselves. Someone else wrote them. We can include them using include statement in C. In Python you have an import statement, but you can include functions written by other programmers and you can call them. That's a great thing to have in the programming languages. I don't think I need to convince anyone of this. Now let's look at assembly. How are we going to solve, or how are we going to do function calls in assembly? Because in assembly we don't have a concept of a function or a procedure. We have memory. We have a program that's just a bunch of instructions, and what can instructions do? They can jump to different addresses. But we don't really have a function. How would you pass an argument? Right? You could think a jump might look to you as a sort of a function call, which in a way it can be, but a function call is much more than a simple jump, of course, because you need to pass on information to the code where you jump to, right? And that's what we're going to look at in this session. How can we solve this? How can we do function calls in Risc-V? To achieve functions in an assembly language, you're going to face two difficult challenges. The challenge of nested execution and the challenge of modularization. Let me first explain this first challenge, nested execution. So what you can have on a high level language, such as C, you can have a function calling another function, calling another function, and so forth. So let's say you would decide on a convention, you would say, okay, we're passing arguments to functions in A0 and A1, for example. Before we do, so a function call is now a jump to a certain location, and we will pass arguments in fixed registers. Well, what you will face if you make this decision, you will face the problem that, well, let's say you have a function A calling a function B calling a function C. All of them will have to provide their arguments in A0 and A1. So what do you have to do when you have to call B from A and C from B? You so have to back up the old values of A0 and A1. So let's look at this in detail. How will we solve this? We will solve this by using a stack. So a stack, a call stack in this case, is a data structure which works by pushing and popping elements. Think about it simply as a physical stack of, for example, books. An empty stack, there's nothing. You place one book on there, you place a second book on there, and a third book on top of that. That's pushing. We are pushing books to our stack. And then if we start removing, the essence of a stack is that you can only remove the top element. So you take the topmost book, you take the second topmost book, and the third one, and then you're popping. That's what is meant by last in, first out data structure. So the last book you put on the stack is the first book you take off the stack. So this is a way, a data structure, a way of organizing memory. And this is a data structure that we will use specifically to allow for function calls. So assembly languages typically provide you with a call stack. Assembly languages typically provide you with a stack pointer. I'll explain in a second. And that will allow you to use a stack data structure, one single stack data structure, which will save all of the information of all our function calls. The stack, whenever we run a program, the stack will be initialized. So the first value of the stack pointer, the start of the stack, will be at a very high address in memory. This is a convention. This is, from a historical perspective, it made a lot of sense. But for now, just know that a stack is always at the high address range of your memory. While the heap, which we will see in next session, will be typically at lower addresses in your address space. So a stack starts, the first value is a top value here at a very high address. And each time you push something to a stack, these squares here are stack elements. Each time we push one, that goes to a lower address on the stack. It grows downwards, we say, because it grows from high addresses to low addresses. It might be opposite from a typical, if you declare an array, you'll typically be incrementing the addresses to go to next elements. In this case, we do the opposite. We start at high addresses, we go to low. To explain stack frames, we need to take a small step back. So remember that I mentioned we could implement a function call simply by doing a jump to a label. And then we could say we're going to pass our arguments in the A registers. We're going to pass our return values also in the A registers. Now, the problem you have here is that, well, there's multiple. The first problem you will face is how do you return from that function? You need to be able to, when your function is done executing, jump back to the code where you were called. This we solve by allocating one register, the return address register, and this will always contain the return value, the return address of the current function you're executing. So a return instruction, it transfers control to some different place in the code, and this return address register will always contain the address to which you need to return the next time you execute return. So the RET, the ret instruction in Risc-V, will jump to the address stored in the return address, the RA register. But let's now think about nested function calls. Let's say we have a function main that calls a function bar that calls a function foo. Well, main calls bar. At that point, the return address will contain some value, some address within main, right? The point where main called bar, that address will be stored in the return address register so that bar can return to that address when it's done. But when bar wants to call foo, he needs a way to save this return address from main, because when he jumps to foo, that return address has to be overwritten so that foo returns to bar and not to main. We only have one return address register. You cannot save multiple return addresses there, but when we're executing in foo, we need multiple return addresses, namely that one of bar and afterwards the one of main. So to solve this problem with the return address, we will use the stack. So whenever we call a function from within a different function, so when bar calls foo, then bar needs to store the return address of main on the stack. And so it will do that. That's what you can see right here. The return address of main is stored on the stack. Now, bar might need to save some other stuff when it calls foo, because foo might use registers that bar also uses. And if bar needs to have the values of those registers before or after the function call to foo, and he wants sure that they're not overwritten, he can save those to the stack. So that would be those bar local variables. One last thing, whenever main calls bar or bar calls foo, it's possible that these have more arguments than can fit in your registers. You can have 100 arguments to a function. Let's say a function with 100 arguments. The first 8 could be passed on with the A registers. The next 92, how will you pass those on? Well, we say we put them on the stack. So let's say bar has 100 parameters, foo has 100 parameters. How does this stack work? Well, main will call bar. To do that, it will first push all of those 92 parameters that don't fit in the A registers. It will push that to the stack. Then it will jump to bar. Before bar can call foo, bar will have to push the return address of main, because whenever he jumps to foo, the return address needs to be overwritten to somewhere in bar. So bar saves the return address of main. It also saves some register that foo might overwrite, and then it calls foo. Now foo will have the same procedure, and foo might call a different function, so it needs to, first of all, some parameters, the 92 parameters that couldn't be passed on were pushed on the stack by bar. Then foo stores the return address of bar before it does a different function call, and it also will need to back up some local variables. And this can keep on going. So how we will achieve this in practice in assembly is simply, we have a stack pointer. This is one register, the SP register, and this is always initialized. So when you start your program, it will be initialized to the top of a stack at a very high address in memory. Every time you want to add an element to the stack, so let's say here at main, the stack pointer is initialized, and then when you want to add an element, you want to decrease the address in the stack pointer by the amount of data you want to reserve. We will be reserving 32 bits, 4 bytes of memory, so 1 word each time we push something to the stack. So with this push operation, we could translate that to decrease the stack pointer. Since we go from high addresses to low addresses, we decrease the stack pointer by 4. That would reserve one of those squares here, and then we could use that square that we just reserved to store some value. So all we need to do to create the stack data structure is to reserve some space in memory where we know the stack will be, and then have one pointer, which is always saved in a register, that points to the top of the stack. That's all we need to do. I've moved myself here for this example. Let's look at a little bit of example code here to illustrate. So we have a function bar. This bar function calls a foo function, right? Simple C code. How can we translate this to assembly? Well, first of all, we have some global variables declared here, so we can declare those in the data section. So we know this already, how this works. Then we have functions. And we declare functions by simply declaring a label. Now the simplest function we have here is the function foo. We're going to make the decision to pass arguments in A0 up until A7. And we will pass return values in A0 and A1. So in this case, we have one return value, an int, will be passed in A0, and we have 2 parameters, A and B, passed in A0 and A1. Then if we look at our foo function, what does the foo function do? All it does is it adds A to B, A0 to A1, and stores the result in A0, which is the register where we have to put our return value. So this is a simple implementation of the foo function in assembly. Now, this ret instruction, this will be a jump instruction. And where will this jump to, right? Well, that depends on who called this function. So if we look at the function calling code, bar called foo, and it called foo by using this JAL, jump and link instruction. What does this do? Jump and link jumps to the label foo and also sets the return address register, one fixed register. It sets this to the address of the next line of code, so to the address of this LW instruction. So whenever ret is executed, it will return to the line after this JAL. Of course, if foo was called from somewhere else, the return address would point to that location. So, by using this combination of JAL and ret, we can call a function and return to from where we were called. Okay, let's look at bar. When bar calls foo, it needs to prepare the correct values in the correct registers. It needs to be sure that an A0 is the value A and an A1 is the value B. Now we made it a little bit easier on ourselves. Bar itself expects C and A0 and D and A1. Since we have the same positions of arguments in the foo call, we don't need to do anything. We know that when bar is called, main will have loaded into A0C and into A1D. We can see that here in the main function. We load X into A0, we load Y into A1. So C is contained in A0. I see this, and D is contained in A1. Right, this is X is the C parameter, D is the Y parameter. And then we jump to bar. So when bar starts, we already know three things. A0 has C, A1 has D, and RA contains the return address, the address of this store word instruction. Now the problem is in bar that when bar wants to jump to foo, this instruction will overwrite the return address. It will overwrite the return address in main with its own return address of LW here. So before we can overwrite this return address, we have to store the old value on the stack. So what we do, we push to the stack. So we reserve 4 bytes on the stack. With this add I instruction, we decrement the stack pointer by 4. This means we reserve 4 bytes on the stack. Then we store the return address to that place on the stack. We jump to foo. When foo is done, we restore, we do the opposite. We load from the stack the value of the return address, of the old return address that will point to main. So we restore that into RA. And then we also unreserve the space on the stack. So whatever space you reserve on the stack, whenever you don't need it anymore, release the space again by, again, incrementing the stack pointer. And the result of this function has to be in A0. This is done in foo. In foo, the result is passed on an A0. Since bar doesn't use A0 and A0 already has the correct result, we don't need to do anything anymore. So we can simply, after restoring the return address, we can simply return to main. Now, of course, this could have been a little bit fake. So we're going to do this again, but now we're going to single step through this code. Great. On the right, you have a nice view of the main memory and the registers. On the left, you have the code, and we will single step through this. So our execution will start when we start the program. What will happen? SP, the stack pointer, Rars will do this for you, will be initialized to a very high value in memory. This address is very high in memory. We don't know what value is stored there. It's still empty, this stack. This is where we will initialize the stack pointer. Now, then we start executing our program. First thing that happens in our program, remember, is we load the values of X and Y in A0 and A1. This is 1 and 2. So our argument registers are now prepared for the call to bar. Then we execute jump and link to bar. So what does jump and link do? Well, it changed this RA value. RA is the register that stores the return address. So it will set the execution to bar. It will jump to bar, but it will also store the return address of SW here, right below this pop-up, the SW instruction, it will store this in RA. So before this, we didn't know what was stored in RA. Now we know the return address is stored there. Next line, in bar, so we jump to bar. What will happen now is we reserve 4 bytes on the stack. So bar will reserve 4 bytes on the stack. So the stack pointer now points to this address. And that means we can use this older address where the question marks are. We can use this to store values. This is now, we consider this memory to be reserved now, to be allocated. That's what we will do. We will store, we will consider this value to be X allocated, and we will now store at the stack pointer the value of RA. So we will store the return address, the address of this SW instruction. We will store that on the stack. Why? Because we're going to call foo now, and by calling foo, we will overwrite our RA register with the return address, with the address of this LW instruction. So by executing gel foo, we overwrite the return address, and then we start executing in foo. This add instruction was executed. This changed A0 to the sum of A0 and A1. So it used to be 1 and 2. Now the sum of those is 3, stored in A0. And then we return. This is the first time we execute the return instruction. Now what do we do? Where do we have to return to? Well, to this address stored in RA by this JAL instruction. This address is the address of the LW instruction, so we know that's where we will have to continue. Now, if we would execute ret right here once more, we would go into an infinite loop. Why? Because the RA register at this point would still point to the same line. It would point to itself and it would loop infinitely. So before we do our return from bar, we need to restore the old return value, the old return address. The return address stored right here before the function call. The return address that points to the SW instruction in main. So we restore that by simply loading the same address on the stack, storing that into RA. So now we restored this 4000044, the address of the SW instruction. We restored that in RA. And now we could execute ret. But before we're going to execute ret, we're going to deallocate our stack space. We don't need that anymore. We've used the stack for what we needed it to back up RA. We restored RA. Now we restore the stack as well. And then we return from bar by jumping to that newly restored return address, which would jump to SW, and it would store the results of A0. This annoying pop-up is on top of it. It would restore the result of A0 into Z using a temporary register. So for our next problem to solve is the modularization part. So we've talked now on how to solve nested execution. We will use the stack, the call stack, to back up variables as a big principle. Now, the second challenge we have to solve is how will we allow functions that I write, functions that you write, function that a compiler writes. How can you make sure that every function can call every other function written by different people, right? Because whenever you call a function, what you don't want to have to do is to go look at the implementation of that function to figure out in what registers do I need to place arguments, in what registers do I need to get the return value, what does this function require me to do. You don't want this. So to solve this problem, we use conventions. We make a deal between programmers, compiler writers. We make a deal to always follow certain rules. Compilers have to do this. If you compile different parts of code with different compilers, you want to make sure that they can still interoperate. And the only way to do that is by having calling conventions. And we will now discuss those calling conventions. So, problem is, right, we expect arguments and return values in certain registers. For example, if you call a library function, what registers will we use to pass the arguments? Where will we expect our return value? And this is the same for the person who calls the code, but also if you're implementing a function. If you're implementing a function, you want to know what registers will be used for argument passing. So we introduce conventions. This is just a convention. So you can write perfectly functioning Risc code without following any of the rules that we will now discuss. You can do that, but your code will only work with your own code. Nobody else can interface with your code. So please write code according to conventions. We will also require you to write code following the conventions for this course. So you will lose grades if you don't follow correct conventions. For Risc-V, the calling conventions that compilers have to follow are explicitly written into this link right here. So let's go over them. These are the rules we will have to follow in the course as well. Arguments. When we compile a function call with arguments, we will pass those arguments in A0 to A7. Now, it could be the case that you have a data type that's bigger than one register. For example, a double is 64 bits in size. On a 32-bit machine, a double needs 2 registers to be stored. So let's say we have this function fun with a double x as an argument. This argument is 8 bytes. It fits into 2 registers. So you will split this argument into the upper and the lower parts, and you will pass it in A0 and A1. So the actual value is a concatenation of these 2 registers. If your data type is even bigger than this, so on a 32-bit machine bigger than 64 bits, or on a 64-bit machine bigger than 128 bits, in that case, you will have to pass by reference. That means you store the value somewhere in memory and you only pass the address. So you're passing it like a pointer. Then, if you run out of registers, if you have 100 parameters to your function, you will run out of register after 8 arguments. All the other you push on the stack before you call the function. Those are the argument conventions. Now for return values, we will also use A0 and A1. So when your function is done executing, your return value must be stored in A0 and A1. Again, the same rule. If you have a return value with 2 registers, you can store it, one part in A0, the other part in A1. If it's bigger than that, you store it in memory and you pass the address. So you return by pointer. So for example, a long double is a 16 bytes in size. That's 4 registers and 32 bits. So you will have to store this long double in memory and just pass the address to the long double as a return value. These are conventions. So whenever you're calling a function that returns a long double, then you know A0 will contain an address. Whenever you call a function that returns an int, you know A0 will return an int. Okay? Please read this document. I will say this again, probably, but read this calling convention document. It's very illustrative. It's only 3 pages long, and it will explain all of this again. But this is important stuff. I'm saying it here on the slide again. Read this. So we have predefined usages for our registers. So not only the A registers are reserved, but we will also see that some registers are ColorSave and some are KaliSafe, to which we will return in a few slides. It also defines data types for C, the fixed sizes, conventions on function calls, so how to do function calls, and we will make an version available to you on the exam. a limited version, not this full, not all these pages, but we will make this available, this document. So this is, for example, something that's in here. When we are compiling C to Risc-V, you are required to make a long double into 16 bytes and a double into 8 and so forth. So as a Risc-V compiler, you would implement the size of function of C, which is a compile time function. So the compiler will resolve this function. You could resolve this with this table, right? But there's much more in here, so please read this document. The only thing you can ignore for this course are the floating point conventions, since we will not be using floating point numbers. It would just add extra complexity. Now I'm going to immediately make an exception to our rule. I just said in CASS we will follow the conventions, the compiler conventions of Risc-V, but we make one exception, and that is the Risc-V convention. You will read this in the document, says that the stack pointer must be 16-byte aligned. That means if you look at the address, that the last two numbers would be 0 and 0, aligned with multiples of 16 bytes. Now, this has to do with some performance reasons for embedded systems. If you want to know in detail why the Risc-V requires this, you could read this interesting discussion on GitHub. But I'm not going to go into detail. The only thing with this is that it's quite annoying to do this, since we are often pushing stuff to the stack, which is only 4 bytes in size. So that would mean we would have to push 16 bytes or reserve 16 bytes, then use 4, and then later maybe use the next 4. It's much more difficult to do it when we're manually writing code. So we will break this convention. In CASS, we will say it has to be 4-byte aligned. So we're always going to increase our stack pointer by 1 word or multiples of 1 word. So 4 bytes or multiple of 4 bytes, but not by 16 bytes, because our words, the values that are typically going to be stored, are 4 bytes in size. Now, you are allowed yourself to follow this convention if you want to. So you can choose to 16-byte align your stack pointer. If you choose this, don't mix it. Don't one function use 16-byte alignment and a different one use 4-byte alignment. Choose one style and stick to that one. If we see you mixing the styles, we're going to assume you didn't understand what the question was. So I'd suggest to choose the 4-byte alignment, but if you want to, definitely you could use the 16 bytes as well. All the solutions and slides will be 4-byte aligned. This is the only convention that we will break in the CASS course. So for us, stack pointer will always be a multiple of 4, but in Risc-V, in fact, the stack pointer will always be a multiple of 16. Great. Now, let's go into ColorSave versus KaliSafe. We've mentioned before that when we're doing nested calls, that it's possible that the function that we're going to call is going to use some of the registers that we were using as well. If you're storing a value in a register and you call a function, then it's possible that this function will overwrite the value in your register. And if you want to make sure you don't lose that value, we've seen before, you can store this value on the stack. But to make it easier on ourselves, on programmers, we've decided to organize our registers into 2 categories: ColorSave and KaliSafe. So, what does this mean? What does this mean? A ColorSave register, so that save with a V, not with an F, means that whenever we call a function, this register can be freely overwritten by the function that you called. So, ColorSave register, for example, the temporary registers, everyone can use them, and you don't have to preserve them. So that means when you call a function, it's possible that this function might overwrite your register, So for a ColorSave register, that's where the name comes from, the caller needs to save the value of this register. Before you call a function, if there is any value in a ColorSave register that you still need after the function call, then you are responsible for saving it as the person who is calling, right? Then you have KaliSafe registers, which is the opposite. A KaliSafe register, for this one, you are guaranteed that when you call a function, that this function will not change the value in that register. So, for example, the S registers are KaliSafe registers. So, when you call a function, let's say I have the value 10 in an S0. When I then call a function, I get a guarantee that when that function returns, the value in S0 is still 10. Because the Kali, so the function that's being called, has to save this value. So if you're writing a function and you want to overwrite or you want to change a value in a KaliSafe register, what you have to do is save that value and restore it later. You can save it on the stack, you can save it in a different register, in a ColorSave register for example, but you have to save it so you can restore it later. So, stored before function call, restored after return, that's the ColorSave registers. KaliSaves are stored after function entry, so whenever you want to be using one of those registers, you store them first and you restore them before you return from your function. So this is all in the calling conventions document, but for a small overview, temporary registers, argument registers, and the return address register are all ColorSave. Remember that when we do a function call, we have to save the return address because doing the function call will overwrite this return address. So it's the responsibility of the person calling the function to save the return address. Then we have some S registers, and these are KaliSafe. And so whenever you are writing a function and you want to use an S register, make sure to save the old value of that S register first before you reuse it. Same goes for the stack pointer and the frame pointer. Another way of looking at this is an invariant. You have to guarantee that at the start of your function and end that the values of all these registers are the same at the start and the end. If you in your function reserve space on the stack, you have to unreserve this space at the end of your function, because stack pointer is a KaliSafe register, which means as a function you're responsible to restore the value of the stack pointer before you return from your function. Same goes for the frame pointer. Now, we haven't gone into the frame pointer into much details. I'll add an extra slide with some general information, but in this course we will not be paying much attention to this frame pointer. It's not strictly necessary to use this, and we have decided to omit it because it adds a little bit of extra complexity that we don't want to spend time on. The last thing we want to discuss in this exercise session is the concept of recursion. So recursion, a recursive function, is a function that calls itself in its body. I think most of you will know this by now. So factorial here is a recursive function. Now, you might wonder how you can implement a recursive function in assembly. And luckily, I'm not going to have to show you 20 different slides now on how to do this. No, this is very easy. If you just follow conventions, you can call a recursive function in exactly the same manner as an iterative or a regular function. You can simply, before you do the function call, what you want to do is to make sure to back up all KaliSafe registers. all ColorSave registers, sorry. You want to back all of those up. Then you can call the function and that's it, basically. So there is nothing special in a recursive function. A last slide I've added here. Let me move myself real quick so you can read it. There we go. I think I moved myself. I hope so. So this last checklist we have here, what to do when calling a function. So you can use this, right? If you're the caller, you want to make sure to save the return address on the stack. First thing you want to do before you call a different function is you save the old return value, because this will be overwritten. You can save all of the other ColorSaved registers, but only if you really need those values. So if you need a value that's in a temporary register, for example T0, if you need this value after the function call, then save it on the stack. What you also want to do then is call the function. It's possible that for this function call you need to push some arguments to the stack as well. That depends on the amount of arguments here. And then when this is done, the function call returns, then you restore all of these ColorSave registers. Also RA, which is just a special ColorSaved register, you want to restore those. So 1 and 2 could be in a single bullet point, but I decided to explicitly split them up. And then as a callee, as a function, what you need to do is, the only thing you actually need to be worried about is whenever you modify a KaliSafe register, the stack pointer, for example, or an S register, that you back it up so that you can restore it at the end of your function. I don't care where you back it up, you can put it on the stack, but you can put it somewhere else too, but you back it up so you can restore it later. That's it on function calling, calling conventions, and the stack. So what I hope you have taken away from this session is, if we go back all the way to the beginning, these two challenges, that you now know how to do nested execution, how we can call functions and how this procedure goes, how we can make sure that we can reuse registers again and again and again in nested function calls, and also how we achieve modularization by using conventions to make sure that pieces of code written by person A can call pieces of code compiled by a compiler without any issues, without needing to look at each other. Just you need to know the function signature, that's it. Good luck with the session.